Dr. Nerz-Stormes. I'm working in my office again. We're working on stereochemistry 5, which was a continuation of stereochemistry 2. And you'll recall in stereochemistry 2, we were working on one stereocenter and kind of learning how to assign them and how to establish relationships. I don't know that I established relationships in my last problem, but I can tell you anything that had the same stereochemistry was the same, and anything that came out to be the opposite were enantiomers. So I want you to think about that a little bit. In this problem, we have two stereocenters, okay? What happens when you have two stereocenters? Well, when you have, and you can have many, you know, or molecules, natural products, organic molecules often have many stereocenters. The maximum number of stereocenters is 2 to the n, where n equals the number of asymmetric carbons. And you'll read about this in my text that I'm writing along with this. This is the maximum number. It's not necessarily the actual number. So what would we expect in this case? In this case, we would expect, which is a very simple, let me change it a little bit, I'll make it an OH. In this case, it's very simple. There appear to be 2 asymmetric carbons. So you would expect 2 to the 2 to be 4. So there should be 4 stereocenters. Stereoisomers. So what should these stereoisomers be? Like if you were kind of plotting it out. Well, what you should get is an RR. I don't know if that makes any sense to you. You should get an SS. You should get an RS. And you should get an SR. That's what we're going to try to generate in our drawings. And again, assigning is going to be your buddy. Assigning is what's going to get you through everything. Okay? I use assigning to just figure out what I've got. So I happened to slap one down arbitrarily. I had no plan in this. When you write a structure, you got a pretty good shot of getting something useful, right? If you have one stereocenter, you got a 50-50 chance of writing the right structure. So I've written this up. Let's assign it. Okay, this center right here, this gives us a little practice assigning. Once again, bromine's going to be number 1. Okay. The H, now look at this. The H in this case is in the front. I did that on purpose. That's going to be number 4. Then you have to compare this carbon to this carbon. Which one is going to win? It should be this one because it has an O on it. That O beats everything on this carbon. So this one is number 2, and this one is number 3. Okay, on that one. I'll do the other one in a different color. Okay, so I trace the circle 1 to 2 to 3. It looks S, but what did you learn? If number 4 is pointing towards you, you have to reverse the designation. All right? So it's that thing where it got behind the board. If I went behind the board on this one, this would really be what? R. This one's really R because that H is not in the proper orientation. Now your textbook will tell you to turn the whole molecule around. Students make a lot of mistakes when they're turning molecules. Students are really good at assigning. They're very good at assigning. All right, let's look at this one. This has 2 centers, so we have to assign both of them. This is number 1 because of the O. The O beats the C and the H that's on that carbon. All right, that H is going to the back. That's going to be number 4. Okay? In this case, what's going to be number 2 if you're getting the hang of this? You've got a C versus a C, but this C has a bromine on it, right? Its first point of difference, highest atomic number. This bromine is going to be everything that's on this carbon. So this is going to be number 2, and this is going to be number 3. Okay, we trace the circle. 1, 2, 3. It looks S. It really is S because where is number 4? It's going back. Okay, now our thing is, we got this one. We just made this compound. Okay? We want to make all the other compounds. How do you make all the other compounds? The way you make all the other compounds is switching 2 groups on each center. Okay, so if I want to draw, for example, and you can do this very easily once you figure the first one out. So say I want to draw the one that's H. I'm going to keep this center exactly the same. So what is the stereochemistry of that center? That center is still R because I didn't change it. But what if I want to make that one the RR? Okay, the RR. Well, I just have to switch 2 groups on the center. The easiest way to do this is to pull the H out, pull the OH out, and switch their positions. So I'm going to put the H out here, and I'm going to put the OH down here. Now, in the beginning, people are just not believers in this. They don't believe it really works. But it does really work. If you trace the circle, right, this is 1, this is 2, this is 3. If you trace the circle, it looks like it's S, but is it really S? No, because number 4 is coming out towards you. So you'd have to turn the molecule around if you want to prove that. So this is really RR. So now we've made the RR. So say you wanted to make, from this one, we'll use that one as our basis. Say you want to make the SS, right? If you wanted to make the SS, you would switch. I'm not even going to do the work anymore, right, because it's so easy. You just switch these guys and keep these the same. If you do this, if you do your work well on the first structure, it is guaranteed you have the SS. And then what do we have left to draw? If we've got the RS, the SS, and the RR, what do we need? We need the RS. Okay, the RS. I'm going to make it from this one. All I would do, right, is keep this center the same. I'll keep that center the same. I'm not even checking these because we did good work at the beginning. I hope. Okay, and then I'm going to switch those two. Put the bromine out. And again, in the beginning, you should check them because you'll just feel a lot better. Okay, so what is this one? This one should be the SS. Am I right? No, no, no. This one should be the RS. Is that right? I feel a little insecure right now. Okay, it is. All right, now, what are the relationships? What is the relationship between RR and SS? The relationship here is that they are enantiomers. The enantiomer of RR is the complete mirror reflection of RR. I always say to students, what does RR see when it looks in the mirror? SS. Okay? It doesn't see SR, it sees SS. So these are enantiomers, non-superimposable mirror images. These two guys, enantiomers. Okay, what else can we say? We can say RR with RS, or these are relationship terms, SR, and SS with RR, RS, or SR. What is their relationship? We have a new relationship. These are not the same because what is the same as RR? What is the same as RR is RR. What is the same as SR? SR. What about these guys? They're not enantiomers, okay? Not enantiomers. They're not the same. But they are stereoisomers. So what are they? These are diastereomers. Okay? And in the world of relationships, of stereochemical relationships, this is the most distant relationship. It's kind of like cousins. I always say enantiomers are like twins, identical twins. Diastereomers are like siblings. They're really like siblings. You can tell them apart. Okay, so we're going to talk more. We have a few more things to do. There's going to be a few more installments in this series. Thank you.